Already I have discussed about zero order and first order reaction in my previous videos. Today, let's know about second order reaction. You will know expression of the second order reaction, graphical representation of second order reaction. I'm going to give you few examples of second order chemical reaction and I will solve few numerical problems. We can define second order reaction as it is a chemical reaction. It is a chemical reaction in which the rate of the reaction is proportional to the concentration of each of the two reacting molecules. The rate of the second order reaction is proportional to the second power of the concentrations of two identical reactants or to the product of the concentrations of two separate reactants. In that case, if the second order chemical reaction is occurred with two identical reactants, in that case we can write it as 2S substrates are converted to P product. In that case, rate of the reaction will be minus ds by dt, that is equal to K into substrate concentration power of 2. So in case of identical reactants, two identical reactants, second order reaction rate is equal to K into substrate concentration power of 2. Now, if the chemical reaction, that is second order with two separate reactants, in that case we can write first substrate is S and second substrate is S prime. They are converted to product P. In that case, the rate of the reaction will be minus ds by dt, that is equal to K into S power of 1 and into second substrate concentration, that is S prime. In that case also power is 1. So 1 plus 1, total power will be 2, and therefore the order of the reaction is 2. Whereas if you compare individually, then the reaction order with respect to each reactant is 1. In one of my previous videos, already I have mentioned that the power law form of rate equation is generally used to determine the reaction order. In that case, rate of the reaction is equal to K into first substrate concentration power of S and into second substrate concentration power of Y, where K is equal to rate constant, S and S prime are the concentrations of the reactants. Exponents of the concentrations of the reactants, those are X and Y, are referred to as partial orders of the reaction. And sum of all the partial orders of the reaction yields the overall order of the reaction, that is X plus Y. Now, in case of second order reaction, the sum of the exponents in the rate law is equal to 2. So, in case of second order reaction, X plus Y is equal to 2. If concentrations of S and S prime at time t is equal to 0 are A and B respectively, that means initial concentrations of S and S prime are A and B respectively, and concentration of each substance that has reacted after time t is equal to x, then remaining concentrations of S and S prime will be A minus X and B minus X respectively. Now, when A is not equal to B, that means initial concentrations of S and S prime are not equal. In that case, rate of the reaction is equal to minus ds by dt, that is equal to K into S, concentration of S into concentration of S prime. Or we can write it as minus dx by dt, that is equal to K into A minus X into B minus X. These two concentrations are for remaining concentrations of S and S prime after time t. Now, if you integrate above equation, you will get kt is equal to 2.303 log b into A minus x divided by A minus b, A into B minus x. Or we can convert this equation as log A minus x divided by B minus x is equal to A minus b into kt divided by 2.303 plus log of A by b. Again, I am writing same equation, that is log A minus x divided by B minus x, that is equal to A minus b into kt divided by 2.303 plus log A by b. It is similar to the straight line equation y is equal to mx plus c. So in this case, y value is log A minus x divided by b minus x, y value, and m value, that means slope, is A minus b into k divided by 2.3, and intercept is log A by b. So c value is log A by b. Now if we plot log A minus x divided by b minus x versus t graph, we can get a straight line with slope A minus b into k divided by 2.303, and y-intercept, that means the value for c, that is log A by b. This is the plot where slope is A minus b into k divided by 2.303 and y-intercept is log A by b. Let's see what happens when A is equal to b. From this equation, we can see that S and S prime react with a 1 and 1 stoichiometry. In that case, St is equal to S0 minus x equal to A minus x, and S prime t is equal to S0 minus S prime 0 minus x, that is equal to B minus x. As A equal to B, A is equal to B, in that case A minus x is equal to B minus x, or St is equal to S prime t at any time t. In that case, rate of the reaction is K into S prime, or we can write it as S into K into S and S and S prime concentrations are equal. So K into S square, and this is similar to the second order reaction with two identical reactants. So we can write in this way, minus ds by dt is equal to Ks square, or we can write it in this way, ds by s square minus ds by s square is equal to minus k dt. If we integrate, we will get this equation, where S0 is the initial concentration of the reactant S at time T0 and St is concentration of the reactant at time T. At time T. Applying the power rule of integration, the equation changes to 1 by St minus 1 by S0 equal to Kt, because if we apply power rule of integration, we found that integration of dx by x square is equal to minus 1 by x plus c, where c is equal to integration constant. So we are getting this value St minus 1 by S0 is equal to Kt. Equation 17 is the final required integrated rate of the equation of the second order reaction. Or we can write 17 equation in this way: 1 by St is equal to Kt plus 1 by S0. That is equation 18. Or we can write 1 by A minus x equal to Kt plus 1 by A. In that case, S0 is equal to A at T equal to 0, and concentration of the substance that has reacted after time T is equal to X. So remaining concentration of S is A minus X. That means St value is A minus X. And 1 by S0 value is 1 by A. S0 value is A. So we can write again 1 by St is equal to Kt plus 1 by S0. Here again we will get a straight line. If we plot 1 by St versus T curve, we will get straight line where slope is K and intercept is 1 by S0. Now we have to determine half-life of second order reaction. Half-life of a chemical reaction is the time taken for the initial concentration of the reactant to reach half of its original value. Already we know that, where T is equal to T half, that means, and St is equal to S0 by T, when substrate concentration is half of the initial concentration. If we put these values, that means T is equal to T half and St is equal to S0 by 2 values in equation 18, we will find this: 1 by S0 by 2 is equal to K T half plus S by S0. This is the equation 18. We are putting T half and St, that is S0 by 2 value, and we are getting this equation. Or we can write this equation in this way: Kt half is equal to 1 by S0 minus 1 by S0 by 2, or T half is equal to 1 by Ks0, that is equation 20, and we can write K as K is equal to 1 by T half S0. So we can say that half-life is inversely proportional to the concentration of the reactant, as T half is equal to 1 by Ks0. Similarly, K is also inversely proportional to half-life. Similar to the first order reaction, the rate constant and half-life of a second order reaction are inversely related. So you can write T half is equal to 1 by Ks0. If concentration of initial substrate concentration is mole per liter, then unit of the rate constant of second order reaction is liter per mole per second. Half-life is inversely proportional to the concentration of the reactant. Already I told that. Half-life increases with the reaction time because of the reactant concentration decreases. as they are inversely proportional. Half-life will be decreased when reactant concentration will be increased. Unlike the first order reactions, the rate constant of a second order reaction can be calculated directly from the half-life if the initial substrate concentration is unknown, because we know that in first order reaction K is equal to 0.693 divided by T half, where there is no value of substrate concentration. K value is not dependent on substrate concentration in case of first order reaction, but in case of second order reaction K value is dependent on initial substrate concentration. I'm going to give you 3 examples of second order reaction. First example is formation of double-stranded DNA from 2 complementary strands. In that case, rate of the reaction is dependent on 2 complementary strands, concentration of 2 complementary strands. Therefore, order of the reaction is second order reaction. Now, second example is decomposition of NO2. In that case, 2 molecules of NO2 are converted to 2NO plus O2. Order of the reaction is 2. Third example is saponification of ethyl acetate. In that case, ethyl acetate plus NaOH are converted to sodium acetate plus ethanol. Rate of the reaction is dependent on both of the ethyl acetate concentration and NaOH concentration. So, order of the reaction is 2. Let's solve few problems. If in a second order reaction 30% of a substrate is degraded within 30 minutes, then how much time is required for the degradation of 60% and 70% of the substrate? As we know that according to the equation 18, 1 by St is equal to Kt plus 1 by S0. Here S0 is equal to 100. If you consider this case 30% of the substrate concentration, that means St is equal to 100 minus 30, that is 70. If we put these two values S0 and St in equation 18, we will find 1 by 70, 70 is St, is equal to K into T, T is 30 minutes, plus 1 by 100, 100 is S0. Or we can write K is equal to 1 by 30, 1 by 30 into 1 by 70 minus 100, that is equal to 30. If we solve this part, we will get 30 divided by 70 into 100. So in this case K is equal to 30 divided by 30, this value, another 30 value, 30 divided by 30 into 70 into 100, that is equal to 1 by 70 into 100. So K value is 1 by 70 into 100. Now we will solve in case of 70% of the substrate degradation. When St is equal to 100 minus 70, that is equal to 30. If we put St value in equation 18 and K value as 1 by 70 into 100, then we will get 70 into 100 into 1 by 30 minus 1 by 100. or we can write it as 70 into 100 into 100 minus 30 divided by 30 into 100. If you solve this one part, we will find this part, or 70 into 70 by 30. You can cut this 100 with this 100, so we will find 70, this 70 value, and 70 that is coming from 100 minus 30 and divided by remaining 30, and that is equal to 163 into 3 minutes. So time required for the 70% of substrate degradation is 163.3 minutes. In this way, you can also solve the problem for 60% substrate degradation. You can calculate in this way. The rate constant for a second order reaction is 0.008 liter per mole second. In this case, K rate constant K is equal to 0.008 liter per mole second. What is its half-life? T half. We have to calculate T half. If initial substrate concentration is 0.1 mole per liter, that means this is the value for S0. Substrate concentration, initial substrate concentration. Substrate concentration as T equal to 0. So in that case, as you know, according to the equation 20, T half is equal to 1 by K into S0. If we put K value and S0 value in this equation, we will get 1 by 0.008, that is the value for K, and 0.01, that is value for S0, that will be 1250 second or 20.83 minute. So half-life of this reaction is 20.83 minute. Thank you very much for watching this video. In my next video, I am going to discuss about third order reaction. Kindly like, share and subscribe this channel and press the bell icon to get the notification.